In this video, we'll take a deep dive into microservices architecture, starting with an understanding of its evolution from traditional monolithic and three-tier architectures. We'll explore how to define and structure microservices, uncover the challenges that come with this approach, and discuss the key deployment strategies and technologies used to overcome those challenges. By the end of this video, you'll have a clear understanding of when and how to implement microservices in your projects. Let's begin by exploring monolithic architecture to understand its limitations and the reasons why the industry is shifting towards microservices architecture. In a monolithic architecture, all the components of an application are integrated into a single unified codebase. This includes the user interface, business logic, and data access layers. While simple and straightforward, monolithic architectures have significant drawbacks. As the application grows, the codebase becomes large and complex, making it difficult to manage and scale. Any change in the code requires rebuilding and redeploying the entire application, which can be time-consuming and risky. Additionally, a single bug can bring down the entire system. To address some of the issues found in monolithic architectures, the three-tier architecture was introduced. The three-tier architecture separates the application into three distinct layers: presentation, logic, and data. The presentation layer handles the user interface, the logic layer processes the business logic, and the data layer manages data storage and retrieval. This separation improves modularity and separation of concerns, making the application easier to manage and scale. Although the three-tier architecture improves modularity and separation of concerns, it still faces several challenges. Despite the separation into layers, different components within each layer are still tightly coupled. This coupling makes it difficult to change or update individual components without affecting others. A failure in one part of a layer can affect the entire layer. For example, if a critical piece of business logic fails, it can disrupt all operations that depend on that logic, potentially affecting the entire application. Development can be slow due to the large monolithic codebase within each layer. Coordination across teams working on different parts of the same layer is often required, leading to delays and complexity. The use of a uniform technology stack across all layers limits flexibility. Teams must use the same technologies in different parts of the application, even if different technologies might be better suited for specific tasks. Testing can be complex due to the interdependencies of components within and across layers. Scaling is typically layer-based, meaning you scale an entire layer rather than individual components. This can lead to inefficient resource use, as you may end up scaling parts of the layer that don't require it. Performance bottlenecks can arise due to the tight coupling within layers. If one part of a layer is slow or inefficient, it can affect the performance of the entire application. In summary, while the three-tier architecture brings significant improvements over monolithic designs by enhancing modularity and separation of concerns, it still has notable drawbacks. Next, we'll explore how microservices architecture addresses these challenges, providing even greater flexibility, scalability, and resilience for modern applications. Microservices architecture is a design approach where a single application is composed of multiple loosely coupled, independently deployable services. Unlike traditional monolithic and three-tier architectures, microservices break down an application into smaller, manageable pieces that can be developed, deployed, and scaled independently. So, the best practices involve splitting the application into services based on core business domains and functionalities. For instance, in an e-commerce application, we might have microservices dedicated to user management, product catalog, order processing, and payment processing. Each service focuses on a specific business capability, ensuring clarity and efficiency in development and deployment. Each microservice should focus on a single business function or responsibility, making it easier to develop, test, and maintain. This principle ensures that each service is dedicated to doing one thing well. Each service should be cohesive, meaning elements that are tightly related to each other and change together should stay together. This enhances the maintainability and clarity of the service. Also, ensure loose coupling between services. Microservices should interact with each other through well-defined APIs, minimizing dependencies. This loose coupling allows services to be developed, deployed, and scaled independently, enhancing the overall flexibility and resilience of the system. Microservices architecture offers several key features that enhance the development, deployment, and operation of applications. Firstly, services can be developed and deployed independently. This means each microservice can be updated, tested, and deployed without impacting other services, leading to faster and more flexible development cycles. Microservices architecture supports decentralized data management. Each service can manage its own database, reducing dependencies and improving data consistency within each service. Polyglot programming is another advantage. Different services can be built using different programming languages and technologies, allowing teams to choose the best tools for each specific task. With microservices, each service has a smaller code base, resulting in faster loading times and shorter build times. This makes development and deployment more efficient and manageable. Microservices architecture enhances resilience. The failure of one service does not affect the entire system, as other services can continue to operate independently, ensuring greater overall system stability. Services can be scaled independently based on demand. This means you can allocate more resources to high-demand services without scaling the entire application, optimizing resource usage. Microservices improve testability. Each service can be tested in isolation, making it easier to identify and fix issues before deployment, ensuring higher quality code. Finally, microservices support continuous delivery. Automated testing and deployment pipelines can be established for each service, enabling faster and more reliable software releases. These features collectively make microservices architecture a powerful approach for building robust, scalable, and flexible applications. While microservices architecture offers many benefits, it also comes with its own set of challenges. Managing multiple services increases the overall complexity of the system. Each service requires its own infrastructure, deployment, and monitoring setup, which can become cumbersome. Managing inter-service communication, including message formats, protocols, and error handling, requires careful planning and implementation. Since microservices often communicate over a network, issues like latency and network failures can impact performance and reliability. Handling these issues requires careful design and robust network infrastructure. With decentralized data management, maintaining data consistency across services can be challenging. Services often need to coordinate to ensure data integrity, which adds complexity. Debugging and monitoring become more difficult with microservices due to their distributed nature. Identifying the root cause of an issue can be challenging when it spans multiple services. Deploying and versioning multiple services independently requires sophisticated CI/CD pipelines and version control strategies. Ensuring compatibility between different versions of services can be tricky. To address the challenges inherent in microservices architecture, a range of deployment strategies and technologies can be employed. Successfully managing a microservices environment requires careful orchestration, robust tooling, and strategic planning to handle complexity and ensure reliability. In this section, we'll delve into the critical strategies and technologies that enable efficient deployment, seamless communication, and maintainable operations within a microservices landscape. Containerization with Docker. Containers encapsulate each microservice with its dependencies, ensuring consistency across development, testing, and production environments. Docker is a popular tool for containerization. Orchestration with Kubernetes. Kubernetes automates the deployment, scaling, and management of containerized applications. It helps manage the complexity of running microservices in production. An API gateway serves as the single entry point for all client requests, providing a unified interface to your microservices. It efficiently handles request routing, directing traffic to the appropriate services while also performing load balancing to distribute requests evenly across available instances. The gateway plays a crucial role in security management, ensuring that only authenticated and authorized requests are processed. It supports protocol translation, enabling seamless communication between clients and services using different protocols. Caching is implemented to enhance performance by reducing latency, while monitoring and logging provide detailed insights into system operations. Additionally, rate limiting and throttling help manage traffic flow, preventing overload and ensuring stable performance. API Gateway also integrates with service discovery and also contributes to fault tolerance, maintaining service availability even when individual services encounter issues. Service discovery is a critical component in a microservices architecture, ensuring that services can dynamically locate and communicate with each other. As services are scaled or instances are added or removed, service discovery automatically updates the list of available service endpoints, enabling efficient routing and load balancing. This dynamic nature ensures that the system remains resilient, adaptable, and capable of handling changes without manual intervention. Load balancing is a critical component in microservices architecture that distributes incoming network traffic across multiple service instances. This ensures that no single server becomes overwhelmed, leading to improved performance and reliability of applications. By efficiently managing the workload, load balancers facilitate seamless scalability, allowing additional servers to be added to handle increased demand or removed when demand decreases. This dynamic distribution of requests not only enhances resource utilization, but also enhances the overall resilience and efficiency of the architecture, ensuring consistent and reliable service availability. Microservices can communicate with each other using both synchronous and asynchronous mechanisms. Synchronous communication often uses HTTP REST, where a service makes a request and waits for a response. On the other hand, asynchronous communication utilizes messaging queues or event streaming, where services send messages that can be processed independently, improving resilience and scalability. Circuit breakers and resilience patterns. Circuit breakers are a vital resilience pattern in microservices architecture, designed to prevent cascading failures across services. In a scenario without a circuit breaker, a failure in one service can propagate backwards, potentially causing other dependent services to fail as well. However, with a circuit breaker in place, the system detects when a service is failing and automatically stops further requests to that service. This allows the failed service to recover without overwhelming it with additional requests, thereby containing the failure and ensuring that the rest of the system continues to operate smoothly. By implementing circuit breakers, we enhance the overall resilience and stability of the application, reducing the risk of widespread outages. Monitoring and logging are essential in maintaining the health and performance of a microservices architecture. Monitoring involves continuously tracking the performance and availability of services, allowing for real-time detection of issues. Logging captures detailed records of system activity, providing insights into the behavior of individual services and the overall system. Together, these tools enable proactive issue resolution, performance optimization, and effective troubleshooting, ensuring that the microservices environment remains robust, efficient, and reliable. We explored the evolution of software architecture, starting with monolithic systems, transitioning through three-tier architecture, and finally arriving at microservices. We discussed how to effectively define the boundaries of microservices, the unique challenges they present, and the deployment strategies and technologies that help overcome these challenges. So now the big question is microservices the right architecture for your project? It's important to remember that while microservices offer significant benefits, they are not a one-size-fits-all solution. Microservices are best suited for complex, large-scale applications where scalability, flexibility, and resilience are critical. For smaller projects, the overhead of managing microservices can outweigh the benefits, making simpler architectures more appropriate. Careful consideration is necessary to determine the right architecture for your project. Thank you for watching and exploring the world of microservices architecture with us. If this video helped you understand microservices better, please give it a thumbs up and consider subscribing for more tech insights. And don't forget to hit the bell icon so you're always in the loop with our latest content. Keep coding, and we'll see you in the next video.